So let's start the high-performance computing platforms. The third topic is FPGA and CGRA. The superscalars, VLIW, vector processors, and GPUs we have discussed are von Neumann computers with machine instructions and program counters. In contrast, these are non-von Neumann computers with no machine instructions or program counters. How to submit the report is the same as last time. As explained in the Introduction to Information Science and Engineering, FPGA and CGRA are non-von Neumann computers. I didn't explain the difference between FPGA and CGRA yet. A feature of non-von Neumann computers is that they do not use sequential machine instructions. But they are not computers if they have no programmability. FPGA and CGRA have different granularity in programmability. FPGA stands for Field Programmable Gate Array. Gates are parts that can express calculations at the bit level. So, we can call it a fine-grained reconfigurable device. The clock period of FPGA is about 6 times larger than that of CPU. On the other hand, CGRA stands for coarse-grained reconfigurable devices. CGRA is designed to manage data with the same degree of granularity as von Neumann computers, such as 32-bit and 64-bit. So, the programmability of CGRA is lower than FPGA. CGRA is based on sacrificing programmability to get high clock frequency as special-purpose hardware. Now, let's try to implement a specific application on FPGA. This is image processing called stereo matching. A depth image is generated from the left eye image and the right eye image. From the result in the lower right, you can see some object is put nearby. With this technique, you can develop an automatic braking system. Here is the specific calculation for stereo matching. The distance to an object can be calculated by finding similar windows in the left and right images and getting the difference between the positions in the images. If the difference is 0, the object is far away. And if the difference is bigger, the object is closer to the camera. The similarity of the images can be calculated by subtracting the red, green, and blue components of each pixel and the sum of the absolute differences. For this computation, we can use the SAD instruction described before. The distance can be calculated by overlapping the left and right images with a slight shift, calculating the SAD of each location, and updating the SAD while increasing the displacement. This figure shows that nearer objects are detected as the calculation progresses from left to right. At this time, the important thing is the edge information. In addition to just calculating the similarity of the images, the location where the edges exist on the left and the right is used as the keystone to interpolate the distance of the blank area. Now, let's consider how to implement the computation on the FPGA. The input is left, right images, and edge information. Since the memory inside the FPGA is small, keeping all the data inside the FPGA is impossible. Therefore, after reading one row of the left image, right image, and edge information, one SAD for each of the 16 consecutive pixels in one row is calculated. In the figure below, many computing units are connected as a tree structure. The top green boxes are for absolute difference, and the rest are for adding 2 inputs. Thus, hardware implementations can compute everything at the same time. By putting 16 sets of this structure in the vertical direction, the SAD of the 16 by 16 area can be calculated in one clock cycle. Furthermore, by shifting the left image to the left and the right image to the right every cycle, you can update the distance information every cycle. This is the whole of the hardware structure in FPGA. Let's calculate the number of arithmetic units. The number of 8-bit registers, subtractors, and exclusive ORs is around 10,000, and the number of tree-structured adders is about 5,000. Let's compare the execution time for generating one depth image from one set of input images with a 2 GHz CPU. Suppose that the SSE2 instruction in the CPU can execute 4 pixel SAD in one cycle, 8 GB SADs can be calculated per second. On the other hand, the FPGA can compute 320 multiplied by 16 multiplied by 16 SADs in one cycle, so with only 33 MHz, 2.7 terasads can be calculated per second. The clock frequency of FPGA is 1/60th of CPU, but FPGA is 320 times faster than CPU. By using FPGA, we can generate 600 depth information frames per second. Modern FPGA can run at 330 MHz, so 6,000 frames per second are possible. Here's a picture of FPGAs. The upper is a typical FPGA board, and the lower is an FPGA for PCI Express in servers. Since it is difficult to implement everything on FPGA, it is popular to connect FPGA to the CPU and use it as an accelerator. In addition to the FPGA board connected to PCI Express, we can purchase SoCs in which the CPU and FPGA are integrated. This is a block diagram for connecting FPGA to the CPU. By mapping the memory on the FPGA board and the registers in the FPGA to the main memory address space of the CPU, it is possible to transfer data to and from the FPGA. After designing the FPGA, writing the circuit configuration to the FPGA, and mapping the FPGA's resources to the CPU's main memory address space, we can write a C program for the CPU that controls the FPGA. Mapping FPGA resources on main memory space can be done by just calling the map system call. By the way, we have two ways to transmit data between CPU and FPGA. The left side is programmed I/O, PIO, where the data is sent one by one using the load or store instructions of the CPU. The right side is the direct memory access, DMA, where the CPU sets the start address and length of the data transmission, and the dedicated hardware sends the data continuously. Also, the upper side is write transaction to FPGA, and the lower side is read transaction from FPGA. DMA write is high speed because it does not wait for the response. On the other hand, DMA read takes more time to wait for the arrival of data. In combining C language and von Neumann computers, statements are converted into machine instructions and executed sequentially. This is the Verilog program for FPGA. Although it looks like C language, it is a hardware description, and all the statements are executed by hardware simultaneously. This is the kernel code for simultaneous SADs, as shown before. There is a loop structure that looks like a C program. But in the case of a hardware description language, this loop structure is spatially expanded in hardware by a circuit synthesis tool, and all iterations are executed simultaneously. Debugging is more difficult than software. However, you can get power-efficient computation. This is an example of how to debug Verilog code by RTL Simulation. All the descriptions run simultaneously, so to check the state of the hardware, we need the waveforms of many wires like this. Also, since it is difficult to identify the wrong description by looking at waveforms, we prepare expected values in advance and compare them with intermediate simulation results to quickly determine inaccurate descriptions. It is completely different from software in that not only the execution result but also the execution time can be accurately simulated. With a 33 MHz clock, you can see that every 30 nanoseconds, 80,000 SAD calculations are performed. After confirming the correctness of the Verilog code by simulation, you need to synthesize the circuit from the Verilog description. This is the result of the synthesis. FPGAs have many small memories called lookup tables that work as logic circuits. Also, the lookup tables are connected by switches and networks. After the synthesis is completed, the next step is placement and routing. In this photo, the CPU and FPGA are embedded in one LSI, and the circuit is mapped to the FPGA part. After placement and routing, you can see how many FPGA resources you have used. This figure shows that 77% of the lookup table is used. The worst negative slack, WNS, is the excess delay time when the target operating frequency is not met. In other words, when using an FPGA, you have to write Verilog codes while considering both whether it can fit into the FPGA and whether you can meet the target frequency. If the target operating frequency is not met, you can look for slow data paths. For example, you'll find long-distance wiring like this, you should change the design to eliminate the slow data path. If you can't fit in the FPGA you have, you can save money and buy a bigger FPGA. Also, newer generation FPGA can generally operate at higher frequencies. The next topic is CGRA. Many copies of several components in the CPU are spatially arranged, and they have no program counters. Traditional programs for CPU are similar to clouded and complicated roads with many traffic signals, and CPU and GPU are similar to old cars that repeat start and stop frequently. But if you can write smart programs with no traffic signals like highways, CGRA can run as a high-speed vehicle with no brake system. The data always goes through the path with no traffic signals, and many calculations are continuously applied to the data stream. In recent years, many engineers and researchers are focusing on CGRAs that can accelerate the processing speed of AI and other applications. The computation speed of CGRAs is much higher than CPU and GPUs. Google already started to use TPU as their own business. They already succeeded in enhancing the performance, reducing power consumption, and improving their profit. As you already learned, the CPU executes many machine instructions step by step. CPU requires many clock cycles due to the narrow data width in each execution. Vector computers including GPU also execute instructions, but have wide data width. One instruction can manage many data, so the power efficiency is higher than the CPU in some specific applications. In contrast to these von Neumann computers, CGRA is one of the non-von Neumann computers. Many calculation units including floating point units are physically arranged in a two-dimensional array, and specific operations are mapped statically on each unit. After the data path among the units becomes ready, the input data go through the CGRA. All of the units perform dedicated operations in a deep pipeline. Finally, the results are generated from the bottom of the network every cycle. In other words, CGRA has no instruction cache, decoder, or branch instruction. Only a flexible data path is prepared and programmed. This is the main reason why CGRA is power efficient. This is an application that we call a median filter. This program loads 9 pixel values from a 3x3 area. RGB values are sorted, and the middle value is selected as the final result. In the CPU case, many instructions are executed for only one output pixel. CGRA can generate multiple output pixels every cycle. This is the transformed program for CGRA. In the previous example, we used a double loop to sort. However, looking at the structure of CGRA, it seems that it needs to be transformed so that data flows in one direction. Therefore, we newly define 5 basic operations that compare 8-bit values and output the value in the specified order. MAX3 takes 3 pixel values and selects the maximum RGB values. Similarly, MID3 outputs the middle value, and MIN3 outputs the minimum value. MAX2 and MIN2 take 2 pixel values as input and ignore C. With these operations, you can remove the double loop. In the program, line 3 takes the 9 pixel values from R0 to R8. Line 4, 5, and 6 correspond to figure A. Finally, we want the middle value of the whole, so we can discard the top right and bottom left corners. If you repeat the above, the maximum and minimum values are discarded to reach figure G. This is the skeleton of the CGRA program written as machine instructions. Max, mid, and min are executed in a 3-input arithmetic unit. A to G corresponds to each state in the previous page. The machine instructions are arranged so that the data flows from top to bottom without the loop structure. The group of instructions in each row is similar to a VLIW instruction. One output pixel can be obtained with only 16 VLIW instructions. And in the case of CGRA, all machine instructions are set at once in many ALUs arranged in a two-dimensional structure. The output pixels are generated seamlessly from below. In other words, it became 16 times faster than VLIW. In addition, memory blocks are connected to line 1 to 3 for providing image data and to line 16 for getting the result. This video visualizes the inside of CGRA. You can see a CPU is running to set up CGRA. And the purple data is continuously provided from the top. Let's compare GPU and CGRA in terms of data movement. A GPU works like a SIMD, but it has a bunch of von Neumann computers, each executing machine instructions. For a multiply accumulate operation such as A and B multiplied by C, all of A, B, C, D must be near the ALU. In CGRA, on the other hand, the ALU only needs the leaf data in the data flow graph. For this reason, there is an advantage in that the cache memory has no line conflict. Also, unlike GPUs, each unit of CGRA does not request data directly to the main memory. By waiting for data to be delivered from the outside, the traffic in the main memory can be reduced. In addition, the data transmission order can be determined in advance without interfering with each other. So it is easy to estimate the performance. This is the convolution included in the tensor library. The red part is the multiply and addition operation. In AI, operations with complicated memory access patterns like this are often used. Modern computers will give you high performance when you arrange the data in a regular manner. However, the memory access pattern of AI programs is quite complicated, so von Neumann computers cannot make full use of the potential. Suppose 300 students board an airplane for a trip. What happens if the first half of the class has an aisle seat number and the second half has a window seat number? A von Neumann computer has a mechanism called cache memory that temporarily stores the contents of the main memory and provides data at high speed in the CPU. In AI programs, the locations of the related data for one output are scattered, so it is easy to push each other out, and the processing speed drops dramatically. Therefore, it is necessary to pack the discontinuous data into a continuous location. It's time-consuming, but you can get high speed finally. However, memory usage is less efficient because the same data should be copied to multiple locations. This means the speed and the space are a trade-off. However, CGRA does not require reshaping for the same convolution. The lower left is the input channel, and the upper left is the weights stored in the host's main memory. The CPU invokes a single DMA transaction. Each unit in CGRA checks the address and imports the data if the address is in the area covered by its own local memory. Broadcasting is available by setting the same area to multiple units. After the burst execution finishes, the results are returned to the CPU. This is the case of backpropagation. Again, the data location is discrete, so copying and packing are required for the CPU. The amount of replicated data is much larger than the convolution in inference. Also, since training consumes much more computation time and power consumption, we need to eliminate learning as much as possible by reusing weights calculated by similar training. This is backpropagation for weights. CGRA can perform tensor calculations without copying data. We also can reduce the reshaping in the input backpropagation. Let's follow one of the CGRAs, IMAX, developed in the Computing Architecture Laboratory. Each unit resembles the structure of a CPU. Let's look at the structure of the CPU again. The diagram on the left is the structure I used to discuss the pipeline at the beginning of this class. It was a 5-stage pipeline, but this structure was wrong because a register file is at the bottom. With this wrong structure, the next machine instruction cannot refer to the previous result. I told you that to design a CPU, the result should be written back to the upper register file. On the other hand, the basic structure of each unit in CGRA is based on the wrong structure on the left side. The register file at the bottom is connected to the succeeding unit. The fundamental difference between CPU and CGRA is the data path related to the register files. Now, let's reshape the basic structure toward IMAX. In general, very few CGRAs have pipelined floating point units because floating point accumulation disturbs the systematic data flow in CGRA. However, FPU is quite important for practical computations. So as in the central figure, IMAX employs multithreading to keep the performance even though accumulation is mapped on FPU. For multithreading, 4 logical units and 16 registers are multiplexed in this way. Furthermore, to keep the logical status of 4 units and 16 registers for the succeeding unit every 4 cycles, double buffering is required. Finally, the number of registers becomes 32. This idea will make it possible to map many kinds of applications on CGRA. And in the right side figure, a 256-bit slave memory interface is attached. In the case of SIMD processors, including GPU, a high-bandwidth master memory bus is best. General CGRAs also get high performance by employing a similar interface. But the target of IMAX is the power-efficient accelerator. Given that IMAX has many local memory blocks and the same data such as input channels and weights should be scattered, it seems better to connect as slave memory to reduce transmission time and power dissipation. After setting a pair of top and bottom addresses to each local memory, just by sending a single DMA stream from the CPU, all local memory blocks are filled in. Many DMAs between the main memory and local memory blocks are optimized and integrated by the compiler based on user directives. During the burst execution of CGRA, the next input stream can be prefetched into the local memory, and the previous output can be drained from the local memory. Let's go on. In the left figure, additional upward data path similar to CPU is attached. By using the blue lines, ALU can refer the result of the first stage, third stage, and the data in the bottom register file. In addition to a simple one-directional execution model of CGRAs, accumulation, read-modify-write of local memory, and address generation based on loaded data from the local memory become available. In the center figure, additional address generator is attached and the local memory is changed to dual port. Now, IMAX can load 264-bit data from independent addresses every cycle. Also, can execute read-modify-write operation every cycle. This physical unit has 4 logical units. 4 octaword loads, 8 double-word loads, or 4 sets of 64-bit read-modify-write can be mapped at once. In the right side figure, pass-through registers are attached. When mapping complicated programs, additional data path for passing through ALU is helpful. 4 physical paths colored by red are pass-through registers. Logical 16 paths can skip the intermediate units. This figure summarizes the calculation patterns supported by IMAX. You can see SIMD dense matrix, random access, sequential updates, accumulation, stochastic FMA, and sparse matrix multiplication. This is an example source code for dense The CPU executes the upper part. IMAX manages the blue part and the red part. After the programmer finishes the algorithm as a C program, the programmer can get the combined binary by the IMAX compiler. The red part has 2 kinds of macros. The upper code is mapped on each physical unit. Each unit gets the result of FMA from the preceding unit, input channel, and weights, for example. Then the results of 4 FMAs are passed to the succeeding unit. The lower code is mapped on the terminal unit where the read-accumulate-write is performed on the cache memory. This is the last part of the mapping result. Each macro is mapped in this way. The black part indicates that the hardware function is not used, and the purple part indicates that the 3-input ALU is used. The left is the matrix multiplication, the right is the convolution. The first and second lines are mostly black because they initialize the counters and address calculations required for sum of products operations. In conclusion, what is essential when using a computer, such as von Neumann computers, FPGAs, and CGRAs, is not the number or performance of ALUs, but the memory bandwidth. Remember that by reusing data stored in internal memory as much as possible, you can reduce external memory references and get high performance and high power efficiency. That's all for today. Don't forget to submit your report. See you next week.